guided practice for section 1.4C. This is about power and the cost of electrical energy. Let's start with number 1. Alfredo sleeps with a 7.5 watt nightlight on. He turns it on before getting into bed and turns it off 8 hours later. So the time is 8 hours. The power is 7.5 watts of that light bulb. So it asks 3 things. Determine the amount of energy used in one evening. What's the cost, right, for a whole year of using it, and then what if you use a different type of light bulb. So let's start with part A. We're looking for the amount of energy. So that's what we're looking for, and I know that power equals work over time, right? So work is your change in energy. So that's another way to write this equation. So I'm going to say the power is 7.5 watts. And we want to find the energy, and we know it's an 8 hour of time. So now you can take out your calculator and you can figure that out. One problem you're going to have, though, is that if you look here, it says in kilowatt hours, and we're in watts. So we want to change this watts to kilowatts. So I'm going to move the decimal place over 1, 2, 3 places so that I can change these units to kilowatts. So now if I do 0.0075 times 8, oops, guess I need new batteries, 0.0075 times 8, I get 0.06 kilowatt hours. Not kilowatts per hour, kilowatt hours is the units of time. So then for part B, energy costs 13 cents. So the cost equals 13 cents per kilowatt hour. And how much is that going to cost for 365 days? So this is how much energy per day. So first I need to know what my change in energy is per year. So to figure it out per year, I've got 0.06 kilowatt hours of energy per day. And I know that there's 365 days per year. Oops, I don't need this word here. So this division sign means per. So now my units cancel, and all I have to do is figure out 0.06 times 365, which is $21.9. And now the last part, determine the annual savings if you replace that 7.5 watt incandescent nightlight by a 0.5 watt LED nightlight. So I'm just going to run through those calculations again. So I've got my power equals change in energy over time. So instead of 7.5, I've got 0.5. So that's going to be 4 kilowatt hours. And we can multiply that by 365. And now let's figure out how much if it's 13 cents. Right, and I forgot to move the decimal place over. The guided practice for section 1.4C about the costs of electrical energy. So you've got Alfredo sleeping with a 7.5 watt nightlight bulb on. He turns it on before getting into bed and turns it off 8 hours later. And then there's a bunch of questions about it to determine the cost. So let's write down what we know. We know the power requirements of this light bulb, the power dissipated, is 7.5 watts. And we know the time that elapses while that bulb is on is 8 hours. So if we're determining the amount of energy used, you have to use the power equation, which is work over time. Another way of saying this is the change in energy over time, and the change in energy is what we're trying to find. So if we're looking for the change in energy, you can write this as power times time equals that change in energy. Notice the units that they want you to work in. We want to get it in kilowatt hours. So we need to turn this into kilowatts. So 7.5 watts, and there's 1,000 watts in a kilowatt. So that's 0.0075 watts. So make sure you do that. Oh, sorry, kilowatts, because the watts cancel. So now if we put that into the equation, right? So we've got our kilowatts times our 8 hours, and that's going to give you 0.06 kilowatt hours per day, right? And that's going to be your change in energy. So that's part A. Part B says that now you've got the cost of electrical energy is 13 cents per kilowatt hour. So if you want to know, and what we're looking for is the cost per year. That's our unknown. So to find the cost per year, right, you have to take how much you use, which is 0.06 kilowatt hours used per day, and you have to say there's 365 days per year. So then the days cancel. This is using dimensional analysis to help you figure this out. That's $21.90 per year. Then part C says, how much would Alfredo save if he replaces it, instead of doing a 7.5 watt bulb, now you've got a 0.5 watt LED nightlight, which uses a different technology and therefore less power. So let's convert that to kilowatts. And we're going to go through the same steps to find the change in energy. Is going to be 0.005 times 8 hours, which gives us 0.004 kilowatt hours per day. And then we need to multiply by 365 days. Per year, then you get 1.46 kilowatt hours per year. And now to find that cost for the year, you need to do 1.46 kilowatt hours per year times that 13 cents per kilowatt hour. And you end up with 19 cents. That's a huge savings, right? You've saved a lot, right? You, instead of paying $21.90, you're only paying 19 cents for that entire year. Okay, so now let's do number 2. Many appliances have 2 power ratings, one for starting wattage and another for running wattage. For example, a refrigerator has a starting wattage of 1350 watts while its running wattage is 550 watts. Can you think of a reason why? Use this reason to explain why the lights in your house sometimes dim when the compressor of the fridge kicks on. So here's the thing. When the refrigerator is not running, it's in the circuit. So let's pretend here's the circuit and here's your fridge. Here's the load. Okay? So if this is your refrigerator, then your refrigerator, when it's off, this here, right, this load, all the coils and everything in it is cold, right? So the resistor is cold. When the resistor heats up, right, as it gets hot, resistance increases. As resistance increases, your current is going to decrease, right? Because the voltage stays the same, right? The voltage is the same always because it's hooked up to your outlet and that doesn't change. So if your resistance goes up, then your current has to go down. And if power is I times V, then when your resistance goes up, which causes the current to go down, then your power decreases. So when it's cold, right? So when you first start, you're going to have a lot of current because it's going to be a cold resistor. So current is up, right? When current is up, power is up. Therefore, your starting wattage might be 1350. So when you heat that resistor, right, as you get current going through it, it gets hotter, and then the current goes down, so your power drops down to 550 watts. Okay? And use the reason to explain why the lights in your house sometimes dim initially. So because you're taking so much current, right? So let's say in another room of your house, here's a light bulb, right? So if this initially pulls a lot of current, then this only has a little bit of that current. It gets less current, and so it'll dim slightly while this is heating up. Once this heats up, everything goes back to normal. Number 3, a central air conditioner in a typical American home operates on a 220 volt. So this is a different circuit because it's going to have a 220 volt instead of a 110 and draws about 15 amps of current. Determine the power rating of such an air conditioner. So power equals I times V. So 220 times 15. So that's going to be a pretty big load, right? So 220 times 15 gives you 3300 watts. The energy consumed if operated at for 8 hours per day. So remember, energy is power times time. So if it's 3,300 watts, which is 3.3 kilowatts times 8 hours a day. So let's divide that by 1,000 times 8. That's 26.4 kilowatt hours. And then the monthly cost, if it's 13 cents an hour. So the cost per month. So we've got the amount of energy that we use per day times the cost. So that gets rid of that. And then we want per month. So 31 days in 1 month. So days cancels. So that gives us 26.4 times 0.13 times 31, which is $106.4. That's added to your cost in the summertime. All right, last one is like looking at this bill. So explain the sample bill shown below to someone who just got their first apartment and doesn't know how to read it. So let's take a look at this. So what you've got here is you've got your usage. So the guys come around, or the meter readers get a meter reading. So this is the number of that's on your meter. Every household has a different number. Here's the actual reading on September 24th, and here was the reading the previous month. So these are the total kilowatt hours that this household used, 672. So this is what they're going to get charged for. So then if you look at the charges, so there's a service charge, it's just a flat rate. Then there's distribution charges, kilowatt hour charges. So for the first 600 kilowatt hours, you get charged $0.04564333, right, for each kilowatt hour, up to 600. So if you multiply those out, it's $27.41. For anything above 600 kilowatt hours, so the other 72, they charge you a higher rate. So they multiply 72 by that higher rate and get a little bit more. So the sum of that is how much they charge you for delivery. But then there's an additional charge done the same way for the supply. So the supplier of the energy then charges you the same way, but notice they charge you more for actually providing that electricity, for generating the electricity. So this is for delivering it, and this is for generating it. So you have the sum of those two charges becomes your overall electric bill. And that's how you read it.